Okay, welcome people of the pre-seminar. It's our pleasure to have Marko Brnovic, who will give us an introduction to quantum double models. Please.
Thank you. Thank you very much for the invitation. I have to say I'm a big fan of the whole pre-seminar concept because I think it gives a great sort of introduction also to people listening, but I think also gives early researchers a great platform to sort of experience and expose themselves to longer talks. So my name is Marko. I'm a student I'm a first-year student at the University of Bologna, and I work with Dr. Elisa Ercolesi. Very broadly, we do models of quantum computation, and one of the models that we're particularly interested is Kitaev's quantum double model. And I'm also a member of the California Marie Curie Actions doctoral program. So I will be talking to you today about two main topics. The first topic will be sort of introductory, just to see maybe pictorially to explain some of the concepts that we will try to generalize later. And the first, also I should say a word of caution is that I'm not a mathematician. I have a background in physics, so I might say some things that are not precise or even correct, or maybe even trivial to you guys. But please interrupt me if there's any problem. It'd be great if this was more of a discussion than just a talk. So I'll be talking to you first of all something that I'm much more familiar with. Well, let's say this connection between physics and mathematics in the quantum double model based on group algebras. And the second one will be based on Hopf algebras and much more closer to what Sebastian will be talking about. And I'll just sort of try to set the stage, define things, and just make it sort of easier to understand, I guess, what he will say. The bigger picture that I'll be talking about today is the sort of connection between topological quantum order that we have in physics and in mathematics. Of course, physics and mathematics are not two disjoint fields. I'm not saying that, but in this naive picture, we have this sort of connection between them where the observables in physics that we look at are sort of governed by algebraic structures in maths. And in particular, something that's important for us today is this idea of quantum memory, which sort of extends from topological quantum order, and how it connects to Hopf algebras. And in particular, towards the end, I'll mention a bit something about the simplicity of those Hopf algebras and how that might complicate things for us. Our story starts with the quantum groups from Drinfeld, and essentially the idea is that we want to generalize the notion of let's say, want to of course look at these things in sort of physical settings. So in maths terms, we're always over the complex numbers. We're always over the field of complex numbers. So this paper, I'm not sure if I guess many of you have seen it, but essentially this paper is the one which introduced first quantum groups and some of the concepts that I'll be talking about today. But so the sort of punchline is we want to quantize things by replacing commutative algebras with non-commutative ones, and in particular sometimes even a bit more general than that. Our setup will be as following. So in full generality, a quantum double model is a quantum spin model, which means I'll describe why it's called a spin model in a bit. But essentially, is defined on a finite oriented graph, and which can be embedded on a two-dimensional surface. However, for just simplicity, I will be talking about a lattice, and I'll fix an orientation such that each horizontal edge has an arrow pointing left to right, and each vertical edge has an arrow pointing bottom to top. And we will then define a quantum spin model based on we'll define something called a dual lattice, and this of course is generalizable to arbitrary graphs. For this, square lattice is just a simple shift, let's say periodic shift in both directions by half an edge. And this, I won't be talking too much about this dual lattice, but I guess it's sort of along the lines of the quantum double. Wherever we have let's say, object A, we have a dual object B, and this is the sort of first, let's say, hint of that. Then we typically define some boundary conditions on this lattice, and in particular, we want to talk about topologies. So we want to look at some non-trivial topological objects, and in this particular case, I just chose to put it on a torus. I hope it's clear that identifying top and bottom and then left and right uh, individually, they give a torus. What we do then is we place qubits, and when I say qubits, I want you to think about just finite dimensional Hilbert spaces, or in this particular case, actually even more specific, is just a copy of a group algebra on each edge, of course, over the complex numbers. To complete our construction, we will add something called the generators of the Drinfeld double, and I'll explain in the following slides what these are. But essentially, these generate the Drinfeld double in both this, of course, the group algebra case and the more general case. At the risk of being too trivial, let's say, a group algebra is just an algebra of a finite group, which is spanned by the group elements formally, and we can, of course, define quantum states. These should be normalized, but let's not worry about that too much, as superpositions of those group states, of those group elements. On a lattice with E spins, we have the overall Hilbert space is just the tensor product of all of these, let's say, these group copies of the group algebra that we put on the edges, and the basis of this Hilbert space is given by all the permutations of the group elements. And of course, the dimension of Hilbert space, let's say, grows exponentially with the number of with the size of the lattice that we put it on. And of course, it matters on the order of the group because that's that's the basis of each site. So Maschke's theorem is, I know some mathematicians will be a bit unhappy. It's a bit more general. It says that for any finite group algebra, if it's over a field whose characteristic doesn't divide the order of the group, then the group algebra is semi-simple. I think I got that right. I'm not sure. Correct me if I didn't. But in this case, since we're always over the complex numbers, it's a pretty just a very succinct statement. So we're working with semi-simple algebras. In some sense, this will make things easy for us, and I'll explain later why this is sort of relevant. We can also define a multiplication, just extending it basically from the group structure, and the representation of that group algebra will just be induced on it by the representation of the finite group. So let's move on to explaining the vertex operators. The vertex operators of a finite group quantum double are essentially composed of these operators that we call L plus and L minus. And L plus is essentially left multiplication, and it's induced again by the group structure. The L minus operator, so the L plus operator we will place with essentially in the orientation such that let's say the arrow ends on the vertex. And if an arrow emanates from the vertex, then we will be talking about an L minus. So this is an important distinction because this will carry on over to every sort of generalization of a quantum double model. So when it ends on a vertex, it will be L plus, and when or multiplication, and otherwise it will be right multiplication with the inverse. We then define the vertex operator as the weighted sum of all of the tensor products of the 4 qubits or the 4, let's say, group algebra copies around the vertex. And you'll notice that these are different depending on the orientation. So also I say weighted sum because I'm just basically summing overall. So here it's important that G is the same for every let's say term in this sum, and then we just divide by the order of the group. And this is a foreshadow for later what will be the Haar integral of Hopf algebra, which will be sort of playing the role of these vertex operators. For plaquette operators, we have something similar. If the operator is on the left side of the plaquette, so this guy in particular has the plaquette on its right side, we will define so-called T plus operator or the dual operator to the left.
Sorry, Marco, there's a question.
Yes.
So,
can you go one slide back, please?
Yes.
Yeah, just this A of V was a bit too fast for me. So in this tensor product, it goes over I in V.
Yes. So
what does that mean?
the I is really just I'm indexing the qubits in the vertex. So it's a bit of a sorry, it's a bit of a not a very easy notation, but essentially it doesn't matter which order I choose it in, or I can choose a particular order starting, let's say, always from the left vertex and going counterclockwise. And that will be, let's say, this will be L1, L2, L3, L4.
Okay, so this is an operator on the tensor product of these 4 Hilbert spaces that you attach at each edge. Okay.
Exactly. Yes. Yes. And it should be known also that this operator is the identity on everything else. So that's
and so it says LG plus minus. So is it plus or minus?
Which one is it? Which one are you talking about? So there's two.
So in A of
yes. So
V.
it depends on what the orientation is. This is sort of compact notation, so that it allows for both L plus and L minus. So if we hit an edge such that the direction is towards the vertex, then it will be an L plus, and otherwise it will be an L minus. So if it's M in the vertex, then it's an L minus.
Okay, thank you.
Yes, no worries. And something similar happens for the plaquettes. It's a different notation, but essentially, if the let's say the edge has the plaquette, or staring down the edge, if we have the plaquette on our right, so in this case we have it on the right, then we have a T plus, and if we have it on the left, and as in this case, we have a T minus. And these are defined by the delta functions in here, but later on when we move to Hopf algebras, they will be defined by, let's say, co-multiplication of the algebra elements. And essentially, the plaquette operator then will be similarly a tensor product of these 4, depending on the orientation. So again, thank you for asking. This is an important clarification that essentially here it's a bit of a different game, because the way that this operator is formed is that we can start at any vertex, and then we go counterclockwise, and everywhere where we do not where we go against the orientation, then we put a T plus, and everywhere we go with, we put a T minus. So one can also think about it that way. Also, the thing that I said before, which is if the plaquette is on the right or on the left, that's the same sort of way of thinking. And we sum over all of the group elements, so all of the elements of the algebra which correspond to the group elements, such that they multiply to the identity. And this is important. You'll see why it's important. Not right now, it might seem very, let's say, arbitrary, but essentially we choose out of the whole group G, we choose only those elements such that the product corresponds to the identity. And then we make the tensor product, and then we average. Oh, sorry, we don't actually average. This shouldn't be there. This is a mistake. Sorry about that. And we do not average. We just choose all of the yes. That's how we define the plaquette operator. But essentially, the main idea is that this will play a role. This is the most important thing to note about this operator. One can check that they commute. In particular, they commute between themselves trivially, but also between each other. One can check that they commute. It's a simple exercise, and they're also projectors. So this allows us to sort of physically think about them as parts of a Hamiltonian. I will describe what that is on the next slide. But essentially, what we can say is that if a state is such that it lives in the +1 eigenspace of this operator AV, then we call it gauge invariant. And if it lives in the +1 eigenspace of BP, then it is called state with a trivial holonomy. And this is the thing that I was talking about on the previous slide, where we have this sort of multiplication equaling identity that is equivalent to asking for a connection. Okay. And then what we do is we define Hamiltonian will be just a sum shifted by some constant just to make the ground state energy 0. It will be a sum of these operators, and it will be a way to measure the energy of the system. And we're particularly interested in the ground state of this Hamiltonian, or let's say the subspace of the Hilbert space corresponding to a 0 energy. or minimizing this Hamiltonian. Now, since A and B commute, they can be simultaneously diagonalized, or we can find a common eigenbasis for them. In particular, we can find states which are both +1 eigenstates of A and B. And this means that we can basically, this Hamiltonian is minimized when we have such a state, and the energy of this, let's say, subspace of the Hilbert space is exactly 0. And we can do this because they mutually commute. In physics, we call this a frustration-free Hamiltonian, meaning that these operators commute. This will become important because this is, again, something that we continue having in the full general quantum double model. As a quick example, I'll give you the simplest possible one, where we have the group algebra, we have the group Z2, and we have the group algebra just being the, basically the, this is what we think about when we think of qubits. So we just have complex numbers in 2 dimensions, and so each site has an algebra, has a Hilbert space of this type, and then the overall Hilbert space is such. We trivially have that L plus and L minus operators are the same because the orientation in this case doesn't matter. If you're wondering why it doesn't matter, it actually isn't to do with the fact that this is an abelian group. It's not even the fact that it's a cyclic group. Both of those things can, like the orientation can matter. It has to do with the fact that it's the simplest possible group. So it's really just the simplest case, but they are not the same between themselves. In particular, in some representation, we can find that the AV operators are exactly the tensor products of all the Pauli X and Z matrices respectively, and then we can work with these operators to find what the ground state space is. This is just, so of course, this might be very trivial when you see it first, but again, it's a simple exercise just to check that these are actually the operators that we were looking at before. Now, if we put this lattice on a torus, we have to look at the algebra that is the algebra of linear operators, essentially, and those operators have to commute with the generators of our quantum double. And the reason why they have to commute is because otherwise they would not correspond to the ground state. So we have to have linear operators which commute, but we also quotient out the trivial, let's say, transformations between them. And these correspond to, well, essentially, these correspond to the fact that if I have a loop on a torus, it can be contracted. If it's a non-trivial loop, then it can be contracted with a trivial loops on a torus on a point. And in particular, G, we can see that it's like closed loops of operators, so of X and Z operators, and only the non-trivial ones are selected. The story here is a bit more, I guess, not involved, but just detailed. I don't want to go into details very much because there's more coming. So essentially, the punchline is that the ground state space here is spanned by, if you will, it's 4-dimensional, and it's spanned by these 2 types of non-trivial loops that we have over a torus. And each loop has, let's say, a corresponding generator, an X and a Z generator. And it is what we call topologically protected. I'll define what topologically protected is on the next slide, but essentially what that means is that it depends on the topology of the lattice or on the boundary conditions that we choose. If we didn't choose periodic boundary conditions, then this wouldn't hold. We would have no non-trivial operators as such, and we would have no, let's say, topological protection. So that's just maybe a flavor of what we are looking for. Now, topological quantum order in general can be very rigorously defined. So this is not some stuff that we talk about, let's say, liberally. But essentially, what it amounts to is the fact that we have these 2 conditions, which the first one basically says that by applying local operators on this lattice, I cannot change this loop to this loop, or I cannot contract this loop by applying local operators. And that's very easy to see when you look at essentially when you look at the first homology group of the surface that you're embedding your lattice on. So that's the first thing. So that's the sense in which is topological, is that you, in order to change, let's say, states, you would need to apply a global operator on it. And the second condition is that a global ground state is equivalent to a local ground state space. And this is less important, but it's more important for some non-trivial lattices and so on. The punchline is here that if we have a quantum double model on an arbitrary finite group, such as the one that I showed before, Z2, then we have topological quantum order, or we have this sort of properties. And the reason why I'm mentioning this is not because I want to get you interested in physics, is because Sebastian's paper has to do with the fact of proving that these generalized quantum double models also have topological order in some sense, or the ground state space is topologically protected. Now, I change flavor completely, and I move into Hopf algebras. And I asked this before, I asked Thomas, and he said that everyone is familiar with Hopf algebras. So I think I'm going to go through these definitions very quickly. I think it's fair. Do you agree?
Yeah.
Or?
Yes, I think we can skip that. Yeah. Also, notice that since
Okay,
we started late, you have easily 10 more minutes. So.
Okay. So let me then move the speed through this basically. Essentially, I'm just defining some notations for. I'm working with Sweedler notations and just all the standard stuff. I have a co-multiplication, a co-unit, and an antipode. And moreover, the example that I'll be giving, or rather this class of quantum double models, will be based. Well, we want them to be complex numbers, but we also want them to be semi-simple, and I'll explain later why. But essentially, we give it a C star structure, and we define we define these opposite actions, opposite multiplication, and co-multiplication, and this will become important a bit later. But essentially, if these opposite let's say actions, or these opposite what do you call them, products coincide, then we call the commutative algebra. And if the co-multiplication and opposite co-multiplication coincide, then it's co-commutative. And in fact, we can also define something analogous to a center, which is the co-commutative elements of this algebra. And we have this duality, so we have a Hopf algebra, and we have its dual vector space. And in particular, the duality is a bit more involved, but essentially we have that the multiplication here becomes the transpose of the co-multiplication in the dual space, and vice versa for the essentially we have also I forgot to say that we have the if we endow, let's say, the opposite products and the opposite elements of this algebra H to basically it, then we have an opposite Hopf algebra, and then we can also make an opposite dual Hopf algebra. We have integrals on Hopf algebras, and essentially Maschke's theorem also applies to Hopf algebras, and it says that if H is finite dimensional semi-simple, then we have a unique Haar integral on that algebra, and this will be important again, as I said, for defining later these quantum double models. But the idea of constructing a quantum double, which we define DH, or to be two co-commutative, and the reason is, well, the physical reason is that we don't want these, let's say, operators that we apply then on, or these, let's say, irreducible representations of these quantum doubles to be we want them to correspond to basically some physical particles, and if they're too co-commutative, then this doesn't really have a nice structure. But Drinfeld found, and this was in the original paper that I showed at the beginning, particular let's say product between the dual of the opposite Hopf algebra and itself, which is called the bi-cross product. Then we get something called a quantum double of a Hopf algebra, and this is really the key sort of let's say object that we'll be working with. And it's worth noting that it's a vector space. This is just the tensor product of the dual and the original Hopf algebra. product structure gives this sort of natural actions, and essentially, I don't want to go too deep into these notations, but essentially, it just goes to show that using this bi-cross product, and this was sort of, let's say, Drinfield's genius, is that using this bi-cross product, one can define a quasi-triangular Hopf algebra, which is not trivial, but it's interesting. Basically, it's an interesting case where some of the physics or some of the, let's say, the interesting mathematics happens, but it's not too nasty, because in general these Hopf algebras don't have to be commutative, don't have to be co-commutative. They can be as basically as none of both of those things as they want, and we can have a very nice multiplication defined on them induced by these actions. In general, we move away from a lattice to a directed graph, and we still have the total Hilbert space is the tensor product of all of the individual copies of the algebra that we put on the edges, and we define the operators. Now, these operators are essentially generalized versions of the operators that I said before, but the left multiplication, the right multiplication with the antipode, and these sort of pairwise, this dual duality pairing between. So here the F is the element of the dual algebra, and A is the element of the original Hopf algebra. And these define basically how H acts on H, and these define how X acts on. X is I sometimes refer to X as this dual Hopf algebra, the opposite dual opposite Hopf algebra. There's some redundancy in the definition, but this is just to say that these two are connected, and it's easy to see if you stare a bit that the antipode is essentially just the conjugation with the antipode just changes between these two. It's also easy to check that they commute between themselves, and we can define for this simple graph the A, or the let's say the corresponding A and B, the generalized A and B operators of these of this graph. And what we do is essentially, and I think Thomas might give an example about this, but essentially we look at this line, and then we start from this line, and then we go in a circle around counterclockwise. And if we hit an edge such that this goes towards the vertex, then we place an L plus. And if we hit an edge that goes away from the vertex, then we put an L minus. So an A operator on this you can think about it as, in a sense, as a circle going from here to here. I don't know if you can see my cursor.
Yes, we can see it.
Okay, great. Because I'm not close. Okay, great. So essentially, what we have is this, and this is against in the suite notation, and the B operator, the generalized B operator, will be essentially just going along this face, going along this plaquette, and anywhere where we go with the orientation of the graph, we'll be putting a T minus, and away from it will be T plus. But for this graph, essentially, it is the same. Now, this holds, of course, only for the chosen orientation. Now, in general, this, of course, this generalizes. I won't be going too much into, because I think I'll leave some space between this pre-seminar and the seminar. But essentially, the same sort of logic follows, and we can define them very generally. And essentially, the way that they act algebra is that they act by left multiplication. But is that they act, if it's going towards the vertex, then they act by this left multiplication, and then it's sort of summed in this Sweetler notation over all of the similar situation. We have this we have this prefactor here, which depends on the antipode of these. But in order not to complicate things too much, essentially, these operators do not commute. They satisfy something called a straightening formula in general. And we can then say that basically this graph supports a DH module structure, which is given by these operators, which is, I think, Sebastian might be talking about them, but it's a type of Jette-Drinfeld module. And it's very nice. It's a very nice tool to work in these in the Hopf algebra quantum doubles. Again, this is just to say that the Haar integral exists on a Hopf star algebra, and we can use it basically to define something what we call, or define a Hamiltonian. To define a Kitaev model, again, we need the commutation between these two operators. So what we do is we take essentially all the algebra elements from the co-commutative elements of H. This is what I was mentioning, is sort of this, let's say, dual center, or the co-commutative center of H. And again, F is in the same thing for this other dual algebra. And then we require that all of them also commute, so that these guys commute between themselves. And then what we have is that these two operators always commute. And of course, if they have support on opposite, let's say, not opposite, sorry, if they do not have overlapping support, in the sense that they do not act on the same tensor products of these Hopf algebras, then they just trivially commute. So the main sort of theorem here, or the main result, is that actually these generalized Hopf algebras, quantum double models, also have topological order, because we can also define a Hamiltonian with them, and we define it using Haar integrals and corresponding Haar functionals. And we can define a Hamiltonian, which is also in the let's say group algebra case, everything sort of follows from there. And again, for this restriction of these A and B operators, we have these much simpler actions where the actions are given by Haar integrals and Haar functionals, instead of this general, let's say, instead of this general, how to call it, the group element action that we saw before. But to sort of foreshadow what Sebastian is going to talk about is, well, we can ask, so far we've been working with Hopf algebras, which are also C-star algebras, which are semi-simple. And the question really is, what if we choose an arbitrary Hopf algebra, which is non-semi-simple? And the sort of the crux of the problem is that if we take a representation of the semi-simple Hopf algebra and the Haar integral, then what we find is the ground state space is essentially the space such that the Haar integral, such that it satisfies this sort of relationship. And we can do this because, well, semi-simplicity of an algebra implies the existence of a Haar integral. And let's say on the physics side of things, this corresponds to the Hamiltonian naturally decomposing our Hilbert space into eigenspaces. And we just have to look at the lowest one. So in some sense, working with semi-simple Hopf algebras is a very trivial problem, because everything is sort of diagonalizable, and you can just look at the, well, not trivial. I'm using the word trivial as a mathematician here. It just means that it's understood. However, this doesn't really work in the non-semi-simple case, because we do not have, in general, a Haar integral. So that's the sort of let's say problem that we see in that, and that's all. If you want to look at more, I would recommend this paper and this paper. And yes, please, any questions? I'm happy to take.
Okay.
Thank you for listening.
Thank you, Marko. Thank you for this nice talk. Are there questions?
Hi, Marko, can you?
Yes.
Yeah. Thanks for the talk. So I've two questions. The first one, could you send me the slides? I really like them. And a more specific question. So in your role, do Hopf algebras play a role? Because it's already quite esoterical, I guess, from a certain perspective, to say, we're now moving away from something very concrete, which is a spin model, to C-star Hopf algebras. Or it's the other way around. Yeah. So do these Hopf algebras play a role in your work? Or
No.
is this now
Yeah, I also should have said that. So we work mainly in group of just group this side of the story that I didn't even mention, but essentially the excitations of we besides the ground state space, we also have some excitations in this Hilbert space, and essentially we can define something. We can basically do computation with those excitations when we look at the unitary evolution of the the excitations in under the action. A picture, basically, we have these excitations on some lattice, on some torus or whatever, and if we braid them, if we move them around, then we can have some non-trivial, essentially, particles arising from this exchange, and that can be used for quantum computation. So that's something that we're more interested in.
Thanks.
Okay, maybe a follow-up question. So you're saying you're mainly looking at group algebras. Yes. So what kind of groups apart from Z2 do you like?
Yes. So I have to say I haven't done a particular project yet, but so Rami, who is also in the audience here, is Elisa's a master student, and he did a few examples with groups like S3 and D4, the dihedral group. Essentially, the sort of goal is to find a group such that something that we call a universal quantum computation is allowed, and there are some strong hints that in order to do that, we have to use non-solvable finite groups. So probably something that we're interested in next is finding, I think the simplest non-solvable finite group is A5, if I'm not wrong, or S5. And so we'll be looking at that kind of stuff.
But it should definitely be finite groups. You're not so much interested in infinite groups, or?
Well, yes, it's difficult to generalize these things to infinite dimensional spaces. Although I'm not an expert on that, I have to say.
Okay. Okay. Are there more questions? Maybe from online people. So if you have a question, just go for it. Doesn't seem to be the case. Then let's thank Marko for the nice talk. Thank you.
Thank you.